Hello everyone, and welcome to today's video lecture, which is on complex numbers raised to real exponents. So this is going to be a video on what happens when we take a complex number and raise it to a power where we're limiting ourselves to situations where the power is a real number. So in today's video, we're going to be studying the behavior of a particular complex function. The function, let's call it w, equals z to the power of x. So in this case, w and z are going to both be complex numbers, but our exponent, denoted by the variable x, is going to be a real number. It's going to be a real exponent. And we're going to see that there are a lot of subtleties to this situation of raising a complex number to a real exponent. So we're going to consider 6 potential cases for our function z to the x. The first case is the one that's most commonly talked about. It's the case where x is a positive integer. The second case will be where x is a negative integer. And we'll see that that changes the behavior of the function. Our third case will be where x is a positive rational number. The fourth case will be where x is a negative rational number. In the last 2 cases, we're going to look at what happens when we raise a complex number to a power x, where x is a positive irrational number. And finally, the case where x is a negative irrational number. So we're going to contrast all these different cases. But first, I'm going to ask you to recall the following. A complex number, z, let's call it, can be written in polar form. So let me draw our coordinate axes in the complex plane. So there's our x-axis and our imaginary axis, I times y. And if we take some point in the complex plane, and we'll call it z, that's our complex number, then z has a certain distance from the origin. This is the modulus of z, which we can denote as r for radius. Okay, so it makes a certain radius and angle with the positive x-axis, and we'll call that angle theta the argument of z. So we can write z in polar form. Z will equal r times e to the I times theta. And this equals, by Euler's identity, r times the cosine of theta plus I times r times the sine of theta. So here what we're saying is that the horizontal component of z, if you want to think of z as a vector, is r cosine theta, and the vertical component of z is r sine theta. So we'll make use of that fact here, because we can then write z to the x equals r, the quantity r, times e to the I theta, so I'll put that in parentheses, all to the power of x. And then by the rules of exponentiation, this would equal r to the x times e to the I theta, close parenthesis, to the x, which would equal r to the x times e to the I times x times theta. So that's what it looks like algebraically. Now let's consider geometrically what raising a complex number to some real power does. So if we have some point in the complex plane here, and it has some radius r from the origin and makes some angle theta with the positive x-axis, we write z equals r times e to the I theta. So now let's consider what happens when we raise our complex number z to a real number x. Well, what happens to the modulus of z, or the radius of z? Well, if x is positive, it's going to increase exponentially by a power of x. So the new radius will be r to the x. And what's going to happen to the argument of z to the x? It's going to be multiplied by x. So we get a new complex number, z to the x, whose radius equals r to the x and whose argument equals x times theta. So this example illustrates the general case. In general, raising z to a real power x will scale the modulus or radius of z exponentially by x, and it will rotate the argument of z from the origin by a factor of x. So now we want to consider the specific behavior of the function z to the x when we set certain conditions, such as x is an integer or x is a rational number. And it turns out that we can best study these cases, we can best study the behavior of z to the x By evaluating the behavior of the function z to the x on one contour in the complex plane, namely the unit circle. So I've drawn here for us two complex planes, both with unit circles centered at the origin, and I've already labeled the one on the left-hand side z equals e to the I theta. I could have written z equals 1 times e to the I theta, but I think it's well known to most of my viewers that that's the equation for the unit circle centered at 0 in the complex plane. And now the unit circle on the right is just equivalent to the set of all points that would be obtained if I take a point z on the unit circle and raise it to some power x. Now why is that so? Because every point on the unit circle has a modulus of 1. Well, 1 to the x just equals 1. So if I take a point z on the unit circle and raise it to some power, it's going to give me a different point on the unit circle. That new point is going to have an argument x times theta. So if I take the set of all points on the unit circle and I raise them all to some power x, the function w equals z to the x is just going to rearrange those points on the unit circle in some way. So this new unit circle, which we can call w equals z to the x, is defined by the equation w equals e to the I times x times theta. And so by studying the behavior of the function w equals z to the x just on the unit circle, again, this is a function from one two-dimensional space, the complex plane, to another two-dimensional space. But we're just looking at the behavior of the function on this particular contour, on the unit circle. By doing that, however, we can ignore what's happening to the modulus of z because that's fixed to equal 1. And we can look at the overall behavior of the function by just focusing on what it does to the argument of z. So we're going to be tracing the behavior of the function as we go through increasing theta. We're going to be tracing w over increasing theta input values. W over increasing values of theta. Okay, so let's see how this would work. Let's take, for example, x equals 2. We're going to set our exponent x equal to 2 here. So what will the function's behavior look like? Well, we're going to write z equals e to the I times theta because, again, we're confining our analysis of the situation to what the function does to this particular contour. So we're setting z equal to e to the I theta, all the points on the unit circle. And then we'll have w equals z squared, or e to the I times 2 theta. Okay? So now if we were to trace out on the unit circle on the left a specific value of theta, so I'm doing that in purple here, I'm making an arc in purple, which is going to be subtended by the argument theta. What would that do in the range of this function, in our function w equals e to the I times 2 theta? Well, it would trace out an arc, which I'm doing in red here, subtended by an angle equal to 2 theta. So that angle there would be 2 times theta. All right, what if we were to keep going? So if I go back to my unit circle in the domain of the function z equals e to the I theta, and I trace out a little bit more, so now I've gone to about pi over 2 radians there, then in the output, or in the range of the function, I'm going to have to trace out a theta equal to twice as much. I'm going to have to trace out a theta equal to pi. By the same logic, if I trace out pi radians as I'm doing on the left side, I'm going to go 2 pi radians all the way around the unit circle in the range of the function. And now that means that if I were to continue increasing theta in the domain, so now I'm going all the way to 3 pi over 2, and then all the way to 2 pi in the domain, I have to go all the way around the circle again in the range. So I'm going to do that here. I'm going to trace out another circle wrapping around here. And that's to cover what I'm doing in the domain, going from pi to 2 pi. In the range, I'm going from 2 pi to 4 pi, or going around the circle one more time. So what have we learned here? Well, when we let x equal 2, as we did in this case, as we increase theta from 0 to 2 pi in the domain, we have to go twice around the unit circle in the range of our function z to the x. So what we have here is a many-to-one function. Going halfway around the unit circle in the domain gets us entirely around the unit circle in the range. Going through the bottom half of the unit circle, the lower two quadrants in the unit circle in the domain, gets us again around all the way around the unit circle in the range. So w equals z squared is a 2-to-1 function. Another way we can see this is that if we pick a particular point in our domain with an argument theta, that point is going to be sent to a point on the unit circle in the range with an argument 2 theta. Now, if I add pi to our original theta, so this is an argument of theta plus pi, that's going to be sent to the exact same point, which has the argument 2 theta plus 2 pi. So we can see that those 2 points in the domain which differ by an angle of pi both get mapped to the same point in the range of the function. So this function is 2-to-1. And in general, we can actually show that when we let x equal a positive integer n, we'll circle the origin n times in the range of the function as we increase theta from 0 to 2 pi in the domain of the function. So we can say w equals z to the power of n is an n-to-1 function when n is a positive integer. Okay, so now let's consider what would happen if our exponent x were equal to a negative integer. So I've drawn here on the left-hand side the domain of our function, the unit circle z equals e to the I theta, and on the right-hand side another unit circle, this one w equals z to the n equals e to the I times n theta. Now when we let x equal a negative integer, we'll track w to the negative n as we increase theta. Well, when we do that, we're going to be moving around the origin in the range of the function in the opposite orientation. So let's see how that works. We'll let x equal negative 2. And if I trace out an angle theta in the domain, I'm going to go in the opposite direction, negative 2 theta, in the range of the function. And hopefully you can see where this is going. If we trace out an angle of pi over 2 in the domain, we trace out an angle of negative pi in the range. If I go halfway around the circle in the domain, I'm going to go all the way around the circle in the clockwise, in the negative direction, in the range. And if I go the full 2 pi radians around the circle in the domain, then I have to go around negative 4 pi radians, twice around the circle in the negative direction in the range. So again, if we circle the origin once in the domain, we circle it twice in the range. And we see that if x is an integer, negative n, then the function w equals z to the negative n is an n-to-1 function. However, there's another important difference between raising a complex number to a positive integer as opposed to raising it to a negative integer, apart from just reversing the orientation of the range. And the key difference is this. W equals z to the negative n, unlike w equals z to the positive n, w equals z to the negative n has a pole at z equals 0. At the point z equals 0, the function w equals z to the negative n is undefined and has no complex derivative. So that's what I've shown here by circling the origin and the range. That's a pole for the function w equals z to the negative n. And the reason for this is that 0, if we set z equals 0, 0 to the negative n, would equal 1 over 0 to the n, or 1 over 0, which diverges. So that covers cases 1 and 2 for our video. Let's now consider the behavior of the function z to the x, where z is a complex number and x is a real number. Let's consider the cases where x is a positive rational number. Or to be more precise, a positive rational non-integer. So let's let x equal positive 1/3 just so we can see what's going on here. And we know that if we traverse an angle theta in the unit circle in the domain of our function, then we're going to traverse an angle of theta over 3 in the range of our function. And by the same logic, if I were to go an angle of pi around the unit circle in the domain, I would go an angle of pi over 3 around the unit circle in the range of that function. Similarly, if I were to go all the way around the unit circle, 2 pi radians around the unit circle in the domain, then the function e to the I theta over 3 will send me 1/3 of the way around the unit circle, 2 pi over 3 radians around the unit circle in the range of the function. So I've gone all the way around the unit circle in the domain, but I've only covered the first third of the unit circle in the range. So what would happen if I started the process over and went around the unit circle again? Well, a second time around the unit circle gives me different theta values. Even though I'm covering the same points, those theta values will be ranging from 2 pi to 4 pi. And that will give me the second third of the unit circle. So that will give me the unit circle from 2 pi over 3 to theta equals 4 pi over 3. And then I would have to go around the unit circle in the domain one full time yet again to cover the unit circle in the range of the output for the function. So I'm doing that here, and I'm showing that this gives me the final third of the unit circle. I've gone from 4 pi to 6 pi in the domain, and I've gone from 4 pi over 3 to 6 pi over 3, which of course equals 2 pi radians in the range of the function. So we say that this function, w equals z to the 1/3, is a three-valued function, or a function with three branches, because we saw that we can go around the unit circle 3 times, and when we do that, each point in the domain in the unit circle maps to one of 3 possible points in the range, before the process would repeat itself and we would be back to the first branch in the range all over again. And this example, which we've worked through, points us in the direction of what happens in the general case, which is that if we raise our complex number z to a rational non-integer exponent, we get a multi-valued function. I imagine most of you can convince yourselves that if we had let x equal 1/4, we would have gotten a 4-valued function, or if we had let x equal 1/10, we would have gotten a 10-valued function, and so on. So this can be contrasted with the previous case, where if we raise a complex number z to some real power x, if x is an integer, we can call it n, we end up with an n to 1 function. Right? We just saw that in the beginning of the video. But now, if x is a fraction of the form 1 over n, we get a n-valued function, or a function with n branches. But as we know, not all rational numbers are of the form 1 over n. So I want to look at the more general case here of what is the behavior of the function w equals e to the I times p over n times theta, where p over n is a reduced fraction. So in other words, p and n don't have any factors in common. They are co-prime with each other. So let's give this case some thought. We want to consider the situation where we raise our complex number z to a rational number p over n. So we're going to look at the function w equals e to the I times p over n times theta. Well, that would just equal e to the I times 1 over n times theta, all raised to the power of p. That's by the rules of exponentiation. And just to see what's going on here, let's make things more concrete by making n equal to 3 again. And now we can just examine the behavior of the function inside the parenthesis before we raise the whole thing to the power p. Well, we already know. Going once around the unit circle in the domain brings us 1/3 of the way around in the range. Going twice around brings us to the second branch of the function. And going 3 times around will give us the third branch of our function for e to the I times 1/3 theta. So let's call that function inside the parentheses e to the I times 1/3 theta. Let's just label it v. So we have v equals e to the I times 1/3 theta, and now we're going to raise this whole expression to the power of p. And again, to make this example more concrete, we'll let p equal 2. So now we can ask what would happen if we were to raise the function v equals e to the I times 1/3 theta to the power of 2. Well, we know that raising this thing to the power of 2 is the same thing as multiplying all the theta values by 2. So effectively, squaring v to get w equals e to the I times 2 over 3 times theta will again give us a function with 3 branches, but each branch will be twice as long because we've doubled theta. So the first branch will now go from 0 radians to 4 pi over 3 radians instead of 2 pi over 3 radians. The second branch will go from 4 pi over 3 radians to 8 pi over 3 radians. And the final branch will go from 8 pi over 3 radians back around again to 12 pi over 3 radians, which again equals 2 pi. So we see that this function, w equals z to the 2/3, which equals e to the I times 2/3 pi, also has 3 branches. And that's illustrative of the general case. which is this. In general, complex functions of the type w equals z to the p over n, where p over n is a reduced fraction, will have n branches. The number of branches is completely determined by what we have in the denominator of the rational exponent. So the fact that this class of complex functions are multivalued can really be a problem for us. It's difficult to do differentiation or integration on a function if the function can equal more than one thing for any given value in our domain. So to make the function w equals e to the I times p over n theta a single-valued function, we have to specify something called a branch cut. And you can watch my video on the complex logarithm, which is on this channel, if this concept is unfamiliar to you. But essentially what we do is we start at the origin here and we draw a ray, which I've selected arbitrarily to be the positive real axis, and we then restrict our theta values to lie between, in this case, 0 and 2 pi exclusive. And as I said in my previous video, once you've made that branch cut, you can't cross it. You can imagine that we've literally cut through the complex plane along this branch cut with a pair of scissors, so that if you were to continue increasing theta, you would fall off the map, in the same sense that the medieval cartographers thought you would fall off the edge of the Earth if you got to the end of the Atlantic Ocean. You might remember, how did we get these multiple branches of the function in the first place? We got it by circling the origin in the unit circle in the domain again and again and again, by restricting our theta value to lying between only 0 and 2 pi, so we're not going to go past 2 pi anymore. We get only one branch of the function in the range. And that's what we're seeing here. I've highlighted it in red. That range over there is going to be equivalent to w of theta, again where theta lies between 0 and 2 pi. And now the function is single-valued. Now if we want to raise our complex number z to a negative fraction, much like our integer case for z to the n where n is a negative integer, if we negate p over n, then in the range of the function that will just reverse the orientation of theta. So what we'll see, for example, is a branch of the function that looks something like this. It'll be coming down in the reverse orientation. So this branch of the function would represent w of theta, where theta lies between 0 and 2 pi in the domain. And again, we would have a pole at z equals 0, because 0 to a negative exponent diverges. So we've covered the cases where our exponent is a positive or negative integer or a positive or negative fraction. And I'm just drawing my unit circles one last time here, so that we can finally consider the behavior of the function z to the x when x is an irrational number. So for the sake of concreteness, let's let x equal the square root of 2. The square root of 2, of course, is irrational. So then we'll have our function z equals e to the I theta, and w equals z to the radical 2, so w equals e to the I times radical 2 times theta. What that means is that if we traverse an angle theta in the domain, we traverse an angle of radical 2 times theta in the range. And if I go all the way around the unit circle in the domain, so if I go around 2 pi radians in the domain, then I'm going to wrap around the unit circle radical 2 times 2 pi radians in the range. So I'm just estimating where that would put me. Let's say somewhere around there. That's radical 2 times 2 pi radians. So note that this function is 1-to-1 for some small values of theta, but as we increase theta, eventually in the range the function wraps back around on itself and becomes a 2-to-1 function, particularly for our values of theta in the domain that lie between 2 pi over radical 2 and 2 pi. Well, that's going to be the first branch of the function. What would happen if we go around the unit circle a second time in the domain? Well, now we're going to get a completely different set of values as the output for our function as we go around the unit circle in the domain, because we're starting at a value in the range whose theta is equivalent to radical 2 times 2 pi. And we're going to go around the unit circle starting from there, another radical 2 times 2 pi radians, and end up somewhere very different. So I've just drawn in yellow the second branch of the function, and the natural question would be, well, how many branches of this function are there? Or another way of asking the question would be, how many times do we have to go around the unit circle to get us back to 0 in the range so that the process can reset itself? And the answer is we never get back to 0. We'll keep going around the unit circle in the range infinitely many times, always landing on a different point. And the reason for this is that the square root of 2 is irrational. That means that there's no way to represent the square root of 2 as the ratio of two integers. There's no way to write radical 2 equals p over q, where p and q are both integers. So in other words, there's no way to evenly divide up this circle if our exponent is the square root of 2. There's no q that's going to return us to our original set of values for our function w equals z to the square root of 2. We're going to keep traveling around and always end up at a different point in the range of the function because radical 2 can't evenly divide the circle. And so this is actually the general case. If x is irrational, the function w equals z to the x is infinitely valued. The function has infinitely many branches. So again, we don't like working with multi-valued functions when we're doing calculus. So once again, we will make use of a branch cut to make the function single valued. So we can make the function w equals z to the x single valued by specifying our branch cut, which here I've just decided to make along the positive x-axis again. When we do that, we restrict our domain to values of theta ranging between 0 and 2 pi, and we're just going to get that first branch of the function. When we go once around the unit circle in the domain, we traverse one branch of the function in the range. And we stop at the point on the unit circle in the range whose theta is equivalent to 2 pi times x, where x is a positive irrational number, in this instance greater than 1. And the last case that we need to consider is the case where x is a negative irrational exponent. And we know from our earlier work, where we let x equal a negative integer or a negative rational number, that for increasing values of theta in the domain, we have increasingly negative values of theta in the range. So I'll draw a new unit circle here in the range, and what I'm showing is that increasing values of theta in the domain give us increasingly negative values of theta in the range until I've wrapped around the unit circle in the clockwise orientation one time. That's the first branch of this infinitely valued function. Secondly, I'm going to circle the origin in the range in yellow to indicate that we have a pole there. That's again because 0 to a negative real exponent is divergent or undefined. So I want to conclude this video by comparing all the different cases for our function z to the x, where z is a complex number and x is a real exponent. So we're going to make a chart here, our different values for x, and then the question of whether there's a pole at z equals 0 and whether the function has a branch cut. So our first case was where x is a positive integer, which we called n. And in that case where x is a positive integer, we don't have a pole at z equals 0 and we don't have a branch cut. Where x is a negative integer, which we can call negative n, we do have a pole at z equals 0, but we have no branch cut. And in both our first and second cases, our function is many to 1. In fact, the functions are n to 1. So I'll just make a note of that there in the branch cut column, that these are many to 1 functions. They don't have branch cuts and they're many to 1. Now the third case that we analyzed was the case where x is a positive rational number, which I'll call here p over n. And if p over n is a positive rational number, then we don't have a pole at z equals 0, but we do have a branch cut. And this function is going to be an n-valued function. It'll have n branches. The fourth case, where x is a negative rational number, which we can call negative p over n, does have a pole at z equals 0, and also has a branch cut, because this is again an n-valued function. The fifth case we looked at was where x is a positive irrational number. And in that case, where x is positive, we do not have a pole at z equals 0, but we do have a branch cut because this is an infinitely valued function. And the final case that we looked at, I'll just extend these lines a little more. The final case was where x is a negative irrational number. And in that case, we do have a pole, we can call the number negative x, and we have a pole at z equals 0, and again we have a branch cut because the function is infinitely valued. So those are the 6 cases that we looked at in today's video. I hope you found this useful. Thank you for watching, and if you did enjoy the video, please like or subscribe to my channel. Thanks again.